Hi everyone. My talk is about parent-infant neurodynamics during social learning. We study biobehavioral synchrony between parents and their offspring. Synchrony can occur at many levels. We can see it in behavior, in physiology, but also in neural states and activation patterns. But these states of synchrony are transient, and we can drift in and out of them several times during the course of social interaction. So we've been interested in the social cues that can trigger and sustain these states of synchrony. For example, gaze, vocalization, and emotions. We're also interested in why humans synchronize. What are the benefits and outcomes? We already know there are positive benefits for affiliation and bonding, but less is known about the effects of synchrony on communication and also on learning, which forms the basis for today's talk. To measure neural synchrony, we use a method called dyadic EEG. This involves concurrently collecting brain signals from parents and infants and using granular causal methods to measure the influence of mother on infant and vice versa. When we study social cues for synchrony, we have to focus on a class of signals called ostensive signals, which convey communicative intent. They tell the infant, I'm online and ready to connect with you. Classically, these signals include eye contact, using the baby's name, and using a prosodically enhanced speaking register called infant-directed speech. In our previous work, we've already shown that one of these ostensive signals, eye contact, is highly efficacious in raising levels of neural synchrony between adults and babies. So recently, we proposed a broader framework which hypothesizes that gaze, as well as other ostensive signals, may have a mechanistic role in resetting the ongoing oscillations in the baby's brain so that they match with and are aligned with that of the parent. These neural oscillations correspond to fluctuations in the excitability of underlying neuronal populations. So when babies' brain oscillations are synchronized to the mother's, this means that they share states of excitability and receptivity. And therefore, in simple terms, this means that the infant is ready to listen when the adult is ready to speak. And in the synchronized state, information may be more optimally transmitted from the sender to the receiver. To study this phenomenon, we carried out this experiment to ask whether neural synchrony potentiates learning between social partners. Why study social learning? Well, social learning is an early developing and evolutionarily important form of learning that has propelled the rise of our human species. Consider caveman Tom here, who's just come across a patch of berries for the first time, and he wants to learn about whether the berries are poisonous or good for eating. He can learn in two different ways. First, through direct experience. Tom can pick the berries and eat them. The problem with this is that if the berries are poisonous, Tom runs the risk of, getting poisoned and dying. There's a second way of learning about the berries, and this involves calling his friend Pete over and saying, Pete, look at these delicious berries. Why don't you try them? And then Tom will fold his arms and watch while Pete picks the berries, puts them in his mouth. And if Pete froths at the mouth and dies, then Tom will have watched and learned the same information through observation, but without risking himself. So you can see why this form of observational learning could confer an evolutionary advantage. We also use social learning in the home. Our infants, just like caveman Tom, are sometimes reluctant to directly engage to learn about new objects themselves or to learn about a new type of food. So it can be hard to get them to try new foods like broccoli. What can we do to get around this? Well, parents can use observational learning. We can take the food, put it in our mouths, make yummy noises and smile with pleasure and go, mmm. And babies watching our positive response would use observational learning to vicariously infer that this food is good for eating and therefore eat it themselves. There's a specific form of social learning called social referencing, and this is where we use information from a social partner to guide or inform our own understanding of a situation, particularly if the situation is novel or uncertain. There are two forms of referencing, instrumental and affective. Instrumental social referencing is also called observational learning and refers to learning from another person's actions or behavior, such as imitation. Affective social referencing involves learning from another's emotions. For example, here we see the visual cliff paradigm. In this paradigm, 12-month-old babies will crawl to the edge of to the middle of the apparatus where there's an apparent edge or visual cliff. At this point, babies will hesitate, and their future action depends on the facial emotions of the parent opposite them. If their mother is smiling and shows a positive, warm, welcoming expression, babies are much more likely to crawl over the cliff and complete the journey towards their mother. Conversely, if the mother shows a negative, fearful expression, then babies are much more likely to freeze and refuse to complete the journey. So in our experiment, we also studied affective social referencing, but we used a novel toy paradigm instead. The experiment was done initially with 90 pairs of mums and dyads who came through the doors into the lab, but after we cleaned out all the data, there were 47 dyads remaining with infants aged 10.8 months on average. Here's how the paradigm went. We gave mothers pairs of novel, ambiguous objects and asked her to demonstrate positive emotion to one and negative emotion to the other. For example, she might look at one object and go, "Oh, this is really nice. I like this." And then look at the other and go, "Ugh, this is awful and yucky. I don't like this." This was called the observation phase, when mothers modeled facial emotions and their babies just watched. Next, we offered babies both objects, and we scored their responses and interaction patterns with each. This was called the response phase. During this experiment, we concurrently collected signals from mums and babies so that we could measure the neural connections within the baby's brain, within the mummy's brain, and between mother and infant. We computed connectivity using phase locking value, and we measured this in the alpha band, which in babies is 6 to 9 hertz. Specifically, we were interested in which neural connections that were active during the observation phase would predict babies' subsequent learning in the response phase. We scored learning in two ways, and this is because some babies consistently selected the negative object. Now, babies who select the negative object can't be said to not be learning because they're still using the emotional responses of the parent to guide their responses. It's just that the response of the child is not socially desirable in our eyes. So as not to confound the valence of the child from the learning per se, we separated these two dimensions into different indices. So valence was a trait level variable which captured the overall bias of the child towards the positive or negatively valenced object, and it was calculated using a cumulative binomial probability function. We then computed the state level variable of likelihood, which was calculated after controlling for the child's individual valence, and it measured on a trial-to-trial basis what the actual pattern of learning was for the child towards their actual target object. We then asked which neural connections during the observation phase predicted these two indices of learning. And these are our main results. On the left, you see the connections within the baby's brain, and then within the mummy's brain, and finally between mother and infant. And this analysis was a correlation analysis between the neural connections measured during the observation phase and the subsequent response of the child. The top row shows correlations to learning valence, and the bottom row shows correlations to learning likelihood, as well as to reaction time. And only the colored voxels are significant. When we did these correlations, we included covariates for movement and infant inattentiveness. And to determine significance, we generated a surrogate distribution by permutating the data to break the temporal contingencies. We also removed spurious correlations that were related to power fluctuations in the data, which are probably driven by motion artifacts. So what you see here in the highlighted voxels have already taken these spurious connections into account and have survived the thresholding. The results are quite clear. We observed a double dissociation in the neural sources that predicted learning valence versus learning likelihood. Specifically, it was the connections within the baby's brain or intra-infant connectivity which predicted positive and negative valence. Conversely, it was only interpersonal connections between mum and baby that predicted trial-to-trial learning likelihood, and they also predicted the learning reaction time of the child. This suggests that there were dynamic changes in levels of interpersonal connectivity during the experiment. So what caused these neuroconnectivity levels to change? When we analyzed the usual suspects, we were reassured to find that increases in maternal eye contact and pitch were positively associated with changes in neuroconnectivity from trial to trial. You might also ask, what explains individual differences in valence? To cut a long story short, we found several important predictors, including maternal-infant temperament match, maternal sensitivity, and also quantity of maternal speech, and this was a negative predictor. Putting everything together, it's clear that there are both intra and interpersonal factors that support social learning. We can think of valence as the intrapersonal factor, which acts as the prior, and it relates to the prior history of the child in interacting with their social partner, which is why it's influenced by things like temperament and maternal sensitivity. And this can be thought of as the internal filter or set point of the child. However, this has to interact with the actual evidence in the moment itself. And this social evidence is mediated through the interpersonal domain, through the interpersonal neural connection between mother and infant, and it's transmitted through these ostensive signals. And it's on the basis of this social information that the baby decides whether to learn or not to learn. To summarize, we found here that neurosynchrony does indeed potentiate learning between parents and offspring. We've seen that ostensive signals like eye contact and speech pitch can dynamically change levels of neural synchrony during interaction and thereby change likelihood of learning. Going ahead, we're very interested in how parental mental disorders like depression and anxiety could change social learning and neuroconnectivity. It remains for me to thank my collaborators, especially Sam Was, and to thank my funders. If you'd like to keep up with us, we have a Twitter account and a website. Thank you for your attention and goodbye.